What we're going to be looking at today is a visual representation of the integral. So at the end of this lesson, you'll be able to evaluate a definite integral by drawing a picture and using geometry. Okay, first of all, before we get into the definition of a definite integral as the area of a region, I want to think back to when we were doing differentiation or taking the derivative. If you recall, when we were taking the derivative and we were looking at it visually, I'm just going to go up here if we have the derivative, and usually we had a picture or something like that. So let's say we were trying to take the derivative of the function y equals x squared and we wanted to find it at a certain point. If you recall, the derivative was just the slope of the tangent line. So that's what that would look like visually. We're looking for the slope of the tangent line, right? When we're looking for a definite integral, what we are looking for is the area of a region. And what actually I would be looking for and we're going to go from like a certain x value to a certain x value. If I'm asking you to find an integral, I'm asking you to find, let's say if I went from this x value to this x value, I'm going to be looking for the area of that region under the curve between the graph and the x-axis. So that's the difference between a derivative and an integral. So if we look at this definition, it says if f is continuous and non-negative on the closed interval a to b are x values, then the area of the region bounded by the graph of f, the x-axis, and the vertical lines x equals a and x equals b is given by this formula. Okay, when you see this integral sign, it's just the s that we've been calling it so far. When you see that, that really is asking, if I'm given a picture, it's asking me for the area of a region, okay, of a certain function, okay, and it's going from x equals a to x equals b. So we're finding the area under that curve, all right? One thing that will be a little bit different if it doesn't specifically ask us for an area, it asks us for the integral. We will keep in mind whether we're above or below the x-axis, so that will make a difference whether my answer is positive or negative. Okay, we're just going to go into some examples here. Now it says for all of these, we're going to draw a picture of the region described, and then using the graph, we will find the definite integral. Okay, when I see this, when it says the integral from 0 to 4 of 3 dx. Okay, 3 is my function. That's my function. Okay, we are going to go from x equals 0 to x equals 4, and we're going to be finding the area under that curve. So if I draw a picture of my function, the picture of the function 3 is just the straight line 3. Okay, so we're just going to draw the straight line 3. I would like to go from x equals 0 to x equals 4. And we're finding the area between the graph and the x-axis. So this is the area that I'm looking at. And then it just says to use that graph to find the definite integral. We're going to be using geometry on most of these problems. I noticed that this is a rectangle, and the area of that rectangle is going to be length times width. So if we just count the length of that rectangle is 4. The width or the height of that rectangle is 3, and so my answer will be 12. So the integral from 0 to 4 of 3 dx is equal to 12. Okay, next we have the integral from 0 to 5 of x plus 3 dx. So x plus 3, this is my function, and I'm going to be going from x equals 0 to x equals 5. All right, and remember the dx is just letting us know that our variable in the problem is x, just in case there were other variables in the problem. So first thing that we're going to do is draw a picture. So the function x plus 3, that is a line. It hits the y-axis up at 3, that's the y-intercept. The slope is 1 because of there's that invisible 1 in front of the x. We're going to go up 1 over 1. Okay, so that's what my line looks like. And then we would like to find the area between that graph and the x-axis from x equals 0 to x equals 5. So that should be a straight line, obviously. Okay, so that's the area that we would like to find. All right, there are two ways to find it. I'm actually going to use probably a different way that you might, but it's totally fine either way. All right, so you might want to, when we find this area, if you would like to, you could find the area of this triangle and then the area of this rectangle and add them together. So that's one way, and if you want to try that way in a minute, that's fine. But what I noticed is if you tilt your head sideways, you will see a trapezoid, and to get us ready for something that we're going to be doing a little bit later this chapter, I'm going to go ahead and find the area of that trapezoid. So, all right, the area of a trapezoid is 1/2 times the height of the trapezoid times the sum of the bases. Okay, so if I'm finding the area of that trapezoid, it's going to be 1/2. If you have your head turned sideways, the height of the trapezoid is going to be this part right here, which is 5. And then the sum of the bases, this would be the first base. The bases are the parallel sides. The first base is going to be 3. And then the second base, if you're not sure what that is going to be, this is occurring at x equals 5. So if you plug 5 in for x in this function, you will get 8. So that base is 8. And so then if we go ahead and work that out, we'll get 8 plus 3 is 11, times 5 is 55, divided by 2, we will get 55 halves. So that would be the integral from 0 to 5 of that function. Okay, and again, you could just as easily made that into a triangle and a rectangle. You're going to get the same answer, so it doesn't matter. You can do either way. All right, number 3, we've got the integral from -5 to 5 of 5 minus the absolute value of x. So hopefully you remember that an absolute value looks like a v. And since this is minus the absolute value of x, I know it's going to be a v turned upside down. And I now also notice it because it says 5 minus the absolute value of x, it's going to touch the y-axis at 5. So we're going to go ahead and draw a picture. So it's going to touch the y-axis at 5. And then I do also know that it's going to touch the x-axis at 5 and -5. And if you weren't sure about that, you could set that equal to 0 to figure out where it's going to be touching. Right, and notice if you plug in 5, you get 0, and if you plug in -5, you also get 0. Okay, so this is my graph in question. We would like to find the area under the curve from x equals -5 to x equals 5. So we actually just want to find the area of this triangular region. So we're going to have 1/2 times the base times the height. That's the area of a triangle. So we're going to have 1/2. The base would be this whole bottom section, which is going to be 10 units. And then the height, how tall is that? That is 5 units. So 1/2 times 10 times 5 is 25. So our integral is going to equal 25. Okay, number 4, we have the integral from -2 to 1 of 3x dx. So again, that's our function. And 3x is a straight line. It's going to hit the the y-axis at 0 because the y-intercept is 0. Our slope is going to be 3, so we're going to go up 3 over 1. And then that's what my line's going to look like. Ooh, did pretty straight there. I'm impressed with myself. Whoops. Okay, so then we're finding the integral from -2 to 1. So starting at -2 and going to 1. Please remember I said that the integral is always the distance between the line and the x-axis. So on this one, we're actually going to be using this section right here and then above. And then one thing that I did say also, we have to pay attention to it whether I'm above the axis or below the axis. So when I find this answer, I will make it negative because it is below the x-axis. So I'm just going to call this region 1 and region 2. They're both triangles. So region 1, we're going to have 1/2 times the base times the height. So we're going to have 1/2. The base goes over 2, and we're not worried about whether I went down 2 or up 2. We just are looking at numbers. And then to figure out how far down that goes, if you just plug in -2 into this function, 3 times -2 is -6, so it goes down 6 units. So 1/2 times 2 times 6 is equal to 6, but we are going to make that negative because it's below the x-axis. All right, region 2 is again a triangle, 1/2 times base times height. It's going to be 1/2. The base is 1 unit. And then the height, to figure out again how high that up it goes, it's over x equals 1. So if you plug x equals 1 in there, you'll get 3. So it goes up 3 units. So 1/2 times 1 times 3 is 3/2 or 1.5. Okay, and then we need to find the total area. So we are going to add those two together. So -6 plus 1.5 would be -4 1/2. And that would be my integral. Notice it didn't specifically ask me to find the area, it did ask me to find the integral. So we are allowed to get a negative answer because notice the area below the x-axis is greater than the area above the x-axis. All right, let's try number 5. We have the integral from 0 to 4 of the square root of 16 minus x squared. Right, you might not notice this, but this is actually the formula for a semicircle. Based on the circle formula, x squared plus y squared equals r squared. So this is going to be my radius squared. So my radius is going to be 4. So it's just a semicircle with center at the origin, with radius 4. So I'm going to go with the radius in all directions, but it's just going to be a semicircle. It's not going to be the whole circle. So that's what I'm looking at. This is asking me for the area under the curve from x equals 0 to x equals 4. So just from x equals 0 to x equals 4. So notice we have just this region right here. And notice if I see that, it's actually, to get that area, it's the area of a quarter circle. And the formula for the area of a quarter circle would be 1/4 pi r squared. So we're going to have 1/4 pi. The radius is 4 squared. And so 4 squared is 16 times 1/4 is 4. So my answer will be 4 pi. So the integral of that one would be 4 pi. Okay, one more. Express the quantity as a definite integral and evaluate the integral. So we actually are going to write our own integral on this one. Find the distance traveled by a train moving at 85 miles per hour from 7 a.m. to 11 a.m. All right, we are going to find a little bit later, and we're going to actually do an activity that shows us this. Distance traveled is just the area under a velocity curve. So if we draw a picture of this velocity curve, oh boy, this train is moving at 85 miles per hour. So it's moving, so if this is a velocity picture, the train, velocity picture, the train is just moving at a constant 85. Okay, we want to find the distance traveled from 7 a.m. until 11 a.m. So we're actually going to be looking for that area underneath that velocity curve. So first of all, how do I represent that? Well, the biggest thing is we're going to have an integral because we're finding the area under the curve. We're finding it from 7 to 11, and we're finding the area under the velocity curve. Well, the velocity was just 85 because it was just a constant 85. And so that would be, and actually we could put a dx or dt based on how I want to. I'm going to put dt because we're dealing with time here. So t would be our variable. So anyway, from here, now we just need to actually find that answer. We just need to find the area under this curve. So the area, again, is just length times width. The length from 7 to 11 is 4, and then the width is 85, and then 85 times 4 would be 340. So 340, and it did say the distance traveled, and we are going miles per hour, so it would be 340 miles for that one. Okay, and hopefully now you are familiar with what a definite integral is using area and are able to evaluate it.